Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hassan bin Shamsul Akmar, A166251 from Group P14. Will be presenting about the result. In this result, we are going to have a model L1, L2, L3A, and L3B together. So in L1, it is a open loop circuit. L2, we have a closed loop circuit. The same model of L1, and L3A and L3B is the same model as L1 and L2, but the addition of disturbance. So in open loop, we are going to find out what is our tachometer gain, the voltage input, the voltage output for our standard target specification, the order of the system, the transfer function GS, and also the output function CS. For the model L2, we are going to use the same model as L1, but now we are going to have feedback so that it will become closed loop. And in this closed loop, we are going to have the transfer function TS, where it consists of GS, KP, KT, and all the resistances here. So we are also going to find the actual percentage error of voltage output and voltage input. What is the corresponding steady state angular velocity when we input the voltage here, the same as L1, and also we are going to find out if there is any overshoot percentage in this model. So in this model L3A and L3B, we are going to compare the value we get from L1 and L2, but now we have the disturbance, so we are going to see what are the effects of the disturbance to our steady state angular velocity in the model. So this is our view of model L1. Basically, we have the voltage input here, where we input whatever value we want. We have the tachometer reading for the motor here in radian per second. We have the actual voltmeter output reading in volts, and also we have the graph voltage versus time. So we have the target specification of angular velocity of 25 radian per second. So in this problem, we are going to use the formula Kt equals to voltage input divided by the angular velocity of our target specification. We input what we want, so we decided to input 15 volt divided by 0.7641 radian per second. This is what we get when we input the 15 volt into the model. We get the tachometer reading, tachometer gain 19.631. So this 19.631, we use it again to find what is the voltage input for this 25 radian per second. So when we input in the model, we get 1.88 volt, and we have to find the tachometer gain again, because this tachometer gain is used for voltage input. What we are going to use is voltage output versus time, so we are going to find tachometer gain for the voltage output. So we get 0.0752. So this is the graph where we have the voltage out here, voltage out, and also here we have the time axis. And from this graph, we have the 60% of the final value at about 1.184 voltage. This 60% comes from the theory, and the corresponding time is 0.0815. And as you can see here, the graph looks like this, so it is similar to first order system. In first order system, it states that first order has no overshoot. So we are going to have 0% overshoot. First order system has this formula GS equals to KDC over A plus S, where we can find the KDC from the formula here, and also A from the formula 1 over T, where T we get from the 60% value of the final value just now. So when we input the value here and value here into the equation, so we get GS this formula, and the lab report required us to find what is the output of the motor when the t equals to 0.081 second just now. So we have to build the transfer function for output with this formula rs multiplied by gs, um, and we have to use Laplace inverse so that from s it is become t, so we can uh, substitute the t here, um, and we got 1.188 volt. It's the same as from the graph, and we plug in into the formula again, formula kt just now, so we get voltage input 3010.115 at 1.188 volt, and the corresponding angular velocity is 15.8 radian per second. So this is our model L2. It's basically the same as L1. We have a voltage input here, and we have a motor here, and we have also the angular velocity graph. Instead of value, we have the graph here, and now we have the tacho generator connected to the summing junction. So this model now become the closed loop function. We have here also the Kp, and here we have Kt. Kp. We use the same voltage input for 190.775 volt, and we get the feedback voltage 3.73 volt in this model. It's different from the model L1. Now we are going to find the voltage error using this formula. So we are going to make the all the resistances here equals to 1, but we cannot set the value to 0 because otherwise the circuit will not work. Then um, we are going to set all the resistances at 1000 ohm. So the last the final formula, we get only voltage in minus voltage out. We get the voltage error here, so we plug in the value, and then from the formula we get the actual percentage error of 0.76%. Now from the model of L2 we see just now, we are going to create the closed loop transfer function Ts. So with Kp here, Kt, Gs, and the summing junction, we can reduce this with block reducing diagram technique. So we get the transfer function 1 plus uh, Kp multiplied by Gs divided by 1 plus Kp multiplied by Gs by Kt. We plug in the value of Gs here, Gs, and this one is Kt. So this one is Gs, and also this one. So we get the Ts formula, and this Ts formula has Kp inside. So this Kp we are going to determine it by using a steady state error, because this one is first order system, so it is a bit difficult to use root locus and root array because we are not sure about the outcome. So from the theory, the transfer function we only has negative real roots because of the graph look like this just now, and we got Kp equals to minus 7.07. So the Kp must be greater than this because according to the root locus graph from the Ts diagram, it should be going to the left in the stable direction. Next, to find Kp, we are going to use 5% of steady state error as the reference. So we get Kp equals to 0.544 for 5% steady state. After that, we plug in the value of Kp, then we use this formula to find the Rv. Next, we input the Rv into the L2 model, and we get the angular velocity steady state of 13.57 radian per second, which is lower than 25 radian per second, but that's the best that we get. So we have the model of L3A here. It's the same as model L1, but the addition of disturbance is there. The disturbance starts when t is greater than 5 seconds. So when we input the voltage in 490.775, the output initially was 25 radian per second, the same as model L1, but after 5 seconds the angular velocity reduced to 24.94 radian per second. We can say that the disturbance reduced the angular velocity about 0.06 radian per second after 5 seconds, because of the disturbance present. Next, we have the model L3B. Model L3B is exactly the same as model L2, but also here we have the disturbance and it starts from 5 seconds. So we are going to input the voltage, the same voltage we used in the previous model, 490.775, and the value of the resistances 1000 ohms. The RV we found from the KP 0.544 at 5%, 5% steady state error. So the output initially is 13.58, is equals to what we have in L2, but after 5 seconds it reduced to 13.51 radian per second. So we can also say that the disturbance reduced the angular velocity about 0.07 radian per second after 5 seconds. So this is our final proportional control design, where Ts equals to this formula, where Kp is here. So Kp must be greater than minus 7.0733 to achieve the stable system. Thank you.